and then the new value you want to put in there. And if your guess was correct, then over here, then it's going to write in the new value. And it does it all in one atomic step. All right? And then the other operation we're going to be using is a read, and that just returns the value that's written in the memory. All right, so the compare and swap operations are going to act like we saw in the previous example. All right, so if there's a bunch of processes wanting to compare and swap, they're going to sequentialize one after the other. And in this talk, I'm going to use a queue type thing to represent the operation sequentializing. Okay, and then what's going to happen is the first one accesses and manages to change the value. And then after that, everyone tries and fails. Oops. Right, so process P over here ended up having to wait in order to try, and then it failed, and now it will have to try again if it really wants to do that cast. So this time it's very sad with a crying face. All right, but if it just wanted to read the value and everybody else wanted to read the value as well, they can all go through in parallel. All right, so the hardware, what really gets sequentialized is changing values on the memory location. Okay, so this is our basic situation. And now I'm going to talk about how we're going to evaluate algorithms in this setting. Okay, so basically what we saw so far were kind of global time steps. All right, so in one time step, one operation gets through. All right, so I mean, if it's compare and swap, right? In one time step, a whole bunch of these reads can go through, but only one compare and swap. Okay, so that's a time step. But we're also going to look at the amount of work that's being done. The amount of work is really, intuitively, it's how much effort everybody is wasting on this thing. All right, so right now, even though only the first process is going to manage to do its operation, the rest of the processes are also trying. So they're wasting effort. All right, so here, I guess throughout this talk, the easiest way to look at work is to think of the size of your queue at every given point in time. All right, so we're going to measure work by just summing up over all time steps. All right, so in this time step, we have 4 processes on the queue. And then in the next time step, we have 3, and 2, and 1, and we end up with having done 10 work units in less time. All right, so this is going to be our measure. And the main operation we're going to focus on is going to be just a very simple use case of something that happens often in shared memory, which is just each process is going to want to update some memory location. What does that mean? It's going to want to read the current value, then locally calculate some modification to that value, and then write in its own calculation. And the writing in, it wants to know that its calculation is still valid, meaning that the value in the memory location hasn't changed yet. Okay, so this is going to be our goal. Okay, and we can quickly run through an example of what could happen if we have n processes that all want to update. Okay, so it depends on the interleaving. If we have n processes and they all want to update, and the first one comes in, reads and does its casts, and then the next one comes in, reads and does its casts, nobody ends up having to wait very long, and all the compare and swaps end up succeeding. But it could also be a very different situation in which everybody comes in and reads at once, and then they all come in and do a compare and swap. All right, so only the first one read a value that hasn't changed yet. So only the first one will actually end up succeeding. And the rest of them will end up doing work but failing. All right? And so we're going to end up with omega n squared work for just everybody trying. Right? And then all the ones that have failed are going to have to try again.
So yeah. What's the intuition when, like, even if somebody is waiting, in some sense they are doing work?
Yeah, so basically they're kind of stuck on the hardware, right? So they've asked the hardware to do something for them, and now they don't know like when it's going to come back, and they end up having to, they're like stuck to the hardware and they have to wait for it. Right? Later we're going to talk about exponential backoff, where they're going to say, I'm not even going to talk to the hardware for now. in which case we're not going to count that waiting period as part of your work, right? They can go and do something else. Okay. So here, we ended up getting n squared time, but n cubed work, right? And this was due to contention, which is just that a whole bunch of people were on the queue at the same time. And now our question is, how do we reduce that? And like Sahil said, maybe we can do waiting periods that don't count as part of our work. So that could be better, all right? And the intuition for that, we're going to take from other models that suffer from similar problems of contention. Okay, so in models like wireless networks and the Ethernet, exponential backoff is often used to kind of lower the amount of contention that you get. All right, so we can go through an example of how it's done in wireless networks and then see if we can adapt that to shared memory. So in wireless networks, you have this graph, directed graph of like where you can send your messages. And what happens is that if more than one message is sent at a time, then all we hear is noise and the message doesn't go through. Right? But if exactly one node sends the message, then it reaches the other side. Okay? And so in wireless networks, in order to get rid of this message failure, which is also called contention, what they do is exponential backoff. Right? So every process is going to maintain a max delay, the maximum amount of time it's allowed to delay itself. And then in every step, it's going to try to send its message. If it fails, it's going to double its max delay, and then uniformly at random pick some delay, some actual value to delay from 1 to that max delay range. All right? So here, everybody started at a max delay of 1, and their actual delay was also 1, and everybody sent their message, and they collided. All right? But then they all doubled their max delay, and uniformly at random picked something in that range. And so some of them are still at 1 and are sending their message together, and some of them are not, so they'll send their message in the next iteration. Okay, and then this goes on, and as you double your max delay, eventually you get to something that allows messages to go through. All right, and in general, when you have a max delay of n, every transmission attempt has a constant probability that it won't collide with anybody. Okay, and so that's what they do in wireless networks, and they do very similar things in Ethernet and a whole bunch of other models. And so now, the very intuitive thing is to say, well, we can do the same thing for shared memory. Okay? And this little bit of pseudocode just does exactly what we just talked about. It maintains a max delay. It tries to do its operation, which in our case is an update. And if it fails, then it doubles its max delay, picks some amount of time to wait, and tries again. Okay? So we can kind of see, this time I have a much more colorful example for you, but it's basically the same thing. Everybody wants to update, but for this example, we're just going to look at their compare and swaps because those are the ones that get stuck on the queue. And here, the first one is done. The second one fails and decides to wait. And like Sahil pointed out, waiting this time is not going to count as part of your work. When you're in the queue, that's working because you're stuck in there. Okay, but when you're outside, you're not working. All right, so this kind of saves, we can see that it saves a whole bunch of work. Those processes could have been in the queue, but they're not. Okay. So really what we save is as the max delay grows, if you think of like a general max delay that there is in a system, as the max delay grows, you get less and less processes in the queue. Right? So this is nice, and it's actually used often in practice for shared memory. Okay? But there's never been theoretical analysis that describes why it does well. Okay, which is kind of weird if we think about it. In the wireless network model, we can analyze it. But in shared memory, nobody has. All right, so now we can ask ourselves, well, what's the difference? Why hasn't anybody done it? And the answer is, I guess, two main differences between the wireless model and shared memory. One is that shared memory is asynchronous. All right, so the fact that I gave you global time steps, that's kind of fuzzy. And usually, whereas in wireless networks you have rounds, in shared memory, the processes can be at very different speeds. Right? So the notion of rounds is kind of vague. And the other thing is, when a process is stuck in the queue, it doesn't even realize that it's stuck until it gets to the end of the queue and tries its operation and fails. Right? So it doesn't notice contention until, well, the length of the queue time has passed. Okay? But the main thing we're going to focus about is the asynchrony part.
So why can't you just notice if you design hardware, so if you wait in the queue for so long, you just leave the queue?
So the thing is, the processes aren't aware that they're actually sitting in the queue. All they know is, okay, my operation hasn't happened yet. But it could be a whole bunch of reasons. Generally, in asynchrony, because processes operate at very different speeds, they don't know. All they know is, okay, well, I haven't gotten any feedback yet, but they don't know the reason for it. Is that?
But why can't you have hardware which does that? I mean, it sounds like a bad design rather.
So I don't know very much about hardware, but I do know that asynchrony, and therefore the delays that processes experience, come not only from hardware, but also from other elements like in the system. And we're going to talk about that later. Right? So there's a bunch of reasons for being delayed, and the process doesn't really know what's happening. Okay? So some reasons can be not due to contention. Right, so, and in general, I guess it might become clearer when we talk about how we model asynchrony. In generally, asynchrony is modeled by assuming you have this adversarial scheduler. And at every point in time, the scheduler is going to pick someone to do the next operation. All right? But it's going to do that adversarially, so that it's going to pick the people who will slow everything down. All right, so for example, we can look at the same example we had before with our exponential delay and see how an adversary can mess us up completely. Okay, so here we're in this state where the first process has already done its operation, and the second one has just failed and increased its delay. All right, so it's sitting outside of the queue. And right now, as we said before, this is saving us a bit of work. Right? So at this point in time, the amount of work expended so far is 2, just these 2 processes, and the time is 1. Yeah.
So when I get returned from the actual queue, do I know how much time passed? Can I just basically estimate the size of the queue by the time I waited and just set my delay accordingly?
So you don't know how much time passed, right? So for example, so here you have this mean adversary, and the adversary stops time for these guys and lets time pass only for this one. All right, and these processes are not aware that this is what's happening. Okay, so time is stopped. Okay, so they're sitting in the queue for longer than they would have. Right, the purple one is now gonna not move. All right, so and it doesn't know if that time passed because it was waiting behind someone or because the adversary was delaying it.
So processor cannot count its ticks, for example?
Processes count its own tick, but its own ticks might go by without receiving any feedback from the hardware.
So I can know how long I waited in the queue. So I can, since I'm doubling my waiting time, I can just set it to a queue size.
So you don't know, because, okay, so here, your adversary kind of stopped you. Sorry. Oops. Yeah. So your adversary stopped you, okay? So you're sitting on the queue longer than the actual amount of contention that happened.
Just remember, this is a multi-process system. So the scheduler is time-sharing that processor with many others. So it can virtualize, it could interleave 27 processes. So you read a time of 7 of real-time clips. You don't know if that's 7 because you waited or because it did useful work during that time on other processes. There's multiple processes running on this system. It's not just, so you can get interrupted, delayed for a second, and then you say, oh, that was some huge amount of time, but actually you didn't waste any work because it was actually useful work of someone else, right? And that doesn't count as a work in here.
Yeah, so just thinking hardware, multi-process system, you think it's virtualization.
Yeah.
Okay. All right, so we have our adversary that can stop time for some people, but let time pass for others, okay? And so what it's going to do is it's going to stand here, stop the queue's progress, and then wait until the delayed processes come back into the queue so that we count them as work. All right, and it can do that repeatedly. Now there's someone that's going to wait longer outside of the queue. The adversary can still say nothing else is going to happen until that one comes back. All right, and so as this continues, what we can see is that the adversary can continuously bring us back to n load on the queue, right? Where in this case our n was 3. Okay, and we get right back up to n cubed work. Okay. All right, so so this is a problem because we know that that exponential backoff works in practice, but our theoretical model doesn't show us why, right? Our theoretical model just says, well, I don't know, the adversary can get us to do as badly as if we didn't try anything, okay? And so now we want to look at, well, maybe we can model it better. Okay, so the first thing we want to do is say, well, where does asynchrony in shared memory come from in order to be able to maybe model it better but still be accurate to what happens in the system? Okay, so there's going to be two concerns, right? One is being swapped out. So useful work might be done, but the current process doesn't see it. All right, so it's being delayed not because of contention, but because of other things that are happening in the system, right? And the other thing, oops, what happened? The other thing that can happen is contention, which we talked about, okay? And so what we're going to do is we're going to separate out these two concerns, all right? We're going to leave the system swapping out issues as adversarial because we don't know how to model them, okay? But contention we can model, and so we're going to do it. Okay, so this was the previous model. You had maybe some processes that are outside waiting, some processes that are ready to do their operation but are being delayed for reasons we don't know of. And then you have your normal delayed by contention. Okay, and what we're going to do in our model is we're going to say, you know, the adversary was able to control all three of these things before. We're going to limit it to control only the ones that are currently wanting to do an operation but haven't reached the hardware yet. Okay, so this is going to be our system delays us for unknown reasons. Okay. Boris, you look very confused.
Suddenly there are 3 boxes and now I'm confused is the main reason.
Okay, well I can tell you a bit more about the model and then we can see if confusion clears up. Okay, so in our model we're going to say we have really 2 sets that an operation that is wanting to be done can be in. It can either be ready, it can either be ready, in which case it's sitting there waiting for the adversary to give it permission to become active. Okay? Once it's active, it's going to sit on our queue and get executed as time passes. The adversary can no longer block the queue. Okay? Yeah.
So when you're in the ready state, are you being counted as well?
No. Ready state is not work. The adversary can delay you, but it's not doing work. Now, when you're in the queue, you're going to manage to be executed right away if you don't conflict with anybody in front of you in the queue. All right? And you're going to conflict, basically, if you're a compare and swap, then you conflict, and if you're a read, then you don't. Okay? And so now we are going to have these global time steps. Once you get into the queue of the hardware, the adversary cannot control you. Okay? But when you leave the queue, you need to go through the adversary in order to put another operation in. Okay, so the adversary always gets to delay you if it wants, I guess, between any 2 of your operations. Okay? Is the model sort of clear? Okay. All right, so now that we have our model, we can finally state our results. Okay? What we show using this model is that, just like we saw before, if you don't do any backoff, then you're at n cubed work. Okay. However, with this slightly relaxed model, we can actually show that exponential backoff does better than not doing anything, which reflects what really happens in practice. Okay, and then using this intuition, we give a new protocol that does better than the classic exponential backoff. Right? So now I know you're all dying to hear about the result of exponential backoff because this is what we talked about so far. But I'm not going to tell you how we got it. Just know that this is the result. And I'm going to focus on our new protocol. Okay. All right, so our protocol is very simple. And it's going to take advantage of the fact that reads can go through in parallel in the hardware, whereas caches can't. All right, so what it's going to do is have each process maintain its own probability for how likely it is to try to compare and swap in this turn. All right. In every step, it's going to flip a coin that's biased according to its that's biased according to its own probability. And if it gets heads, it's going to try to compare and swap. All right. If it doesn't get heads, if it gets tails, it's only going to read. Right? In either case, if it compares and swaps or it gets tails, it's going to read after its coin flip to see whether the value in the memory location has changed. Right? And if it has changed, it's going to lower its probability to try again in the next step. And if it hasn't changed, it's going to be a little bit more confident in itself. Okay? So the idea is that if the value in the memory location you're trying to access isn't changing very often, you can be more confident that contention isn't happening. Okay.
So if you fail CAS, we don't change probability.
So if you fail CAS, sorry. So, oops, why is it moving? Okay. If you fail the CAS, if your CAS succeeds, you return.
Right. Of course.
You don't continue.
Of course.
If your CAS fails, then you read.
Also, it's else for that if. Okay.
Yeah. Sorry. I guess it's unclear. This should be just you always read. Okay. If your CAS fails, you want to know what the new value is. You know that it changed, but you want to know now what it is. And in any case, because your CAS failed, you already knew that the value has changed, so you're going to lower your probability. Okay.
I think so. It's got it.
Okay. Okay. So this is our new protocol. Yeah.
So when the values change, does that mean that you go and do more computation internally now that the values change? Or
Yeah.
That's a separate?
Yeah, so I left that out here because in this model we usually assume that local computations are incredibly quick compared to any shared memory operation. Right? So yeah, so you read the new value, you quickly calculate your new value, and yeah. Okay, so now the natural question is, well, is this protocol better than exponential backoff? And I already kind of spoiled the answer for you. Yes, it is, but we're going to see why.
Now, one question.
Yeah.
By change, do you mean you're just comparing bitmaps, bits, or
So,
is there some
so you can think of it as we don't have the ABA problem. Okay, we always know whether there has been a successful compare and swap between the last time you read and now.
So this is a true change.
It's a true actual. Someone has gone in there and changed the value. Okay. Okay. All right. So the first thing we want to do in order to get intuition for whether this will work better is, well, we want to see, where do we get work from? What is heavy? All right. So just remember, our work is going to be the sum over all time steps of the size of our active set, or our queue. Okay. And we know that every process wants to do needs to do at least one cast, right? That's going to be its successful compare and swap, after which it's going to terminate. So we already know we need at least n time. Where's my? Yeah, we need at least n time. All right, but we also know that there's other operations happening. There's reads, there's more failed compare and swaps, right? Everything can happen. So we're probably going to be more than that. But if we imagine what is the state of the queue at all times is this. There's one compare and swap, and that compare and swap is going to succeed, whereas all the other operations in the queue are reads. Okay? If we imagine that this is the situation, what's going to happen is as follows. On time step 1, this compare and swap is going to go through, and that process is going to return. Right? On the next time step, all of these reads will be executed in parallel. Why? Because they don't conflict with each other. All right? So what's going to happen is we're going to have one successful cast every other step. Right? So we're going to have a successful compare and swap followed by a whole bunch of reads that are happening in parallel. And then again, one successful compare and swap. All right? Right? Because we said our reads don't conflict with each other, and therefore they can go through in parallel.
You're saying this is the best case.
Yeah. So this is the best case scenario. If this happens, then we have n time steps, and in each one of them we have n things that are sitting on the queue. Okay, and so we get n squared work. Okay. But I mean, we don't know. We have these probabilities of whether we're going to compare and swap or
Probably I don't understand your model still. Why can't adversary, just basic case, it sees a bunch of reads in some user reads, and then it basically has the processors which had those reads done. Do this, then allow them to enter the queue. So now, and then basically.
No, okay, so you're right. So what the adversary, if the adversary knew, okay, so this is true, and I haven't mentioned it yet. Okay, if the adversary knew what operation each process has chosen to do on its next step, a perfect strategy for it to do would be to say, everybody that wants to read gets to read, okay? And so their probabilities are going to be creeping up, right? Because they don't see any change in the system, they're raising their probabilities. And then it's going to stop everybody that wants to write until nobody else wants to read, right? And let everybody go at once. And now, so this is this case, right? You always have, or like a lot of your steps have all compare and swaps in the queue, right? And then you're right back to n cubed work. All right, so you're right, this can happen. And so we limit the adversary, and I have it in like 2 slides or something. We limit the adversary to only know the probability of your coin flip, but not the actual result. Okay. Okay, so is everybody okay with this? If my queue is full of compare and swaps, then I'm going to take n cubed work, right? Okay, so the adversary's goal, like we said, is to get our probabilities to cast to be very high so that most of the time our queue is full of compare and swaps. Whereas our goal is to have those compare and swap probabilities relatively low. In particular, we want 1 over n, so that in every step we'll have approximately 1 compare and swap going through. All right? But like Boris said, we need this assumption. We need the adversary not to be able to see the results of our coin flips. All right? So it can know the current probability that each process has, but not the future. Right? It can't know what will the coin end up being. All right? Okay. So now, given these conditions, this is our main lemma that's going to prove our good running time. The lemma says that every process, regardless of what the other processes do, makes at most 4 cast attempts. All right? So really what it says is the adversary tried to get all of us to waste a lot of compare and swap attempts, and it can't. It does some like ridiculously small constant. All right? So this is what we're going to try to show. Okay, so what we're going to do is we're going to consider a single process. Okay, so before we had all of the processes, now we're only going to look at it from the point of view of the purple one. Okay, this process, what does it know? It knows its own probability for compare and swap. It knows its result of the coin flip, although the adversary doesn't know that. And even though it's sitting on the queue, it doesn't know who is sitting on there as well, and it doesn't know how many. All it knows is right now it's trying to do its operation, and oh, it got its feedback. It failed. It doesn't know why. Yeah?
Just double check. Every process starts with an initial probability of 1?
Yeah.
Okay.
Everyone starts high just for the optimistic assumption that maybe there won't be anybody there, and then you can go through. Okay. And then it lowers its probability, and it changes. So what's really happening here is the adversary is sitting there deciding what processes to place before the purple one. Right? So the adversary can sort of choose by placing processes ahead of the purple one whether or not the purple one will see a change or not. Okay? And like Boris mentioned, we have this assumption that the adversary doesn't know the actual results of their coin flips. It just knows the probabilities. So it can put some weight ahead of the purple process in order to kind of influence whether it will go, it will see a change or not. Okay? And so we're going to call this weight rho. All right. Okay, so now we can model P's progression through the execution as this state transition system. Okay, basically we're going to give P states. Well, it's in state I if its probability is 2 to the minus I. Okay, and we can kind of dissect what this state transition system means. This row over here is the weight that the adversary can put in front of the process. Okay, so if it puts enough weight, so if the value has changed, which is with probability P, then regardless of what the result of P's coin flip is, it will go to the right. Okay, its probability will decrease. Right? However, if that doesn't happen, so if rho was not big enough to make a change in the value, then what will happen depends on P's coin flip. All right, so this is P's coin flip, and it's really the probability that it actually decides to execute a compare and swap. Right? Because if the value hasn't changed, so we're here, and it executes a compare and swap, then it succeeds. Right? And if the value hasn't changed and it decides to read, then it just goes to the left. Right, so we're going to label these transitions go to the left and go to the right. Okay, and we're going to use this to do the rest of our analysis. Okay, so we have our lemma. We want to say that in expectation, P does at most 4 compare and swap attempts. All right, we're going to look at P, and we're going to look at the sequence of states that it visited throughout the execution. Okay? And we're going to split up this sequence. Really what we want to do is we want to count the amount of compare and swaps that happened as it transitioned through these states. Right? So we're going to split it up into 3 chunks. And we're going to analyze each one separately. Okay? So the first chunk is going to be, we're going to call it the initial chunk. And that's just going to be the first appearance of every state that P visits is going to be in this chunk. Okay? And then we're going to have the rest of the execution except for the last step, which we're going to analyze separately. Okay, so, well, some of this is easy to do right now, right? So this chunk of the execution is going to be visiting each state exactly once, all right? And in each state, the probability that it will cast is exactly 2 to the minus I for state I, all right? So we have the sum of 2 to the minus I, as I increases, and we know this is a geometric sequence and is less than or equal to 2. All right? Then the last step, we know that in the last step, what you did for your final operation is you successfully compare and swapped. Right? So that's one compare and swap right there. All right? And now we have the rest. Right? So we're almost done, really. We know the beginning, we know the end. There's just this mysterious chunk in the middle. Okay? And so the rest of our analysis is going to focus on this. So before we actually do the analysis, we're going to make one useful observation. Okay? If we look at one state, and we think of the number of times that P in its execution transitioned left from the state to another. Okay? And then we look at the number of times that it's transitioned right to this state. Okay, so we're looking at this little transition over here. Okay, we know that it had to have transitioned left at least as many times as it transitioned right to that state. Why? Simply because, well, in order to leave that state, it had to have gotten there first. Okay, that's a very, very, very simple intuition, right? And what that's going to mean for us is we're going to actually separate it out so that we're only going to look at steps going left, and we're going to account for the cost of going right just by pretty much multiplying our cost by 2. Okay? All right, so back to our main problem. We have this lemma. What we had left is to prove that the rest of our execution doesn't do too many compare and swaps. All right, and we have this useful claim that says the number of times for every state, the number of times I go left from it is greater or equal to the number of times that I go right to it. Okay. And again, just as a reminder, we have this state transition system, which again, this is controlled by the adversary and is the probability that we'll see a change. And this is the probability that we'll flip heads and do a compare and swap. All right, so now I'm going to add just a little bit of notation, right? I said we're going to look at the left steps. Okay, so I'm just going to number them. So I'm going to look at my execution, and I'm going to see every time I transition to the left, I'm going to just index it. Okay, so this this term is going to correspond to the cost remaining in our execution after the j step that went left. And S of j is just going to be the state we're in after we went left. Okay? And my claim is that this is it. This is our analysis. Okay, so we can kind of go through it more slowly and try to dissect it. This is the cost of going right from Sj, from, say, we're here, from Sj back to the right. Okay? So this, we're accounting for the future. We know that we're here now, and we're saying, well, maybe in the future I'll want to go back. So just in case, I'm going to already account for that cost. Okay? And then this part says, well, now I could, if I go left, I could be leaving the system, right? And that depends on my coin flip. My coin flip, I have a 2 to the minus I probability of just leaving the system. Okay? Now, if I didn't, then I have the rest of the cost of the rest of the execution to account for. Okay? So this is our equation, and it ends up being that if you work this out and simplify it, you get that this is less than or equal to 1. Okay? So I'm not going to go through the simplification of this, but this is what happens. It's relatively easy to see because this constant and this constant are the same. Okay. All right, so regardless of Sj, just because in every step, if you think of us opening it up, at every step we have these values being the same, we're going to be less than 1. Okay?
So,
yeah?
So rho is kind of measuring like the influence of other jobs in the queue?
Okay, so right, so the influence of other jobs I've abstracted away. I've abstracted it away here. I'm saying the adversary can influence the weight that it gives me for the value having changed, right? But what I said here, I'm not limiting rho at all. The adversary can put any probability it wants over there, which is not actually true. It's more relaxed. What?
Isn't rho changing with time?
So sure. So even if the adversary changes rho on every step, all right, and I'm allowing it to change it arbitrarily, anywhere between 0 and 1. Okay. Now I'm looking at the steps that I know ended up going left. All right. So in that case, I know that I'm sort of conditioning on the value didn't change. Okay. All right. So regardless of what the adversary picked as this value, as this row, I know that if I'm here, then the value didn't change. Right? Okay. Anyway, so now we have a cost of less than 1 for this whole the rest of the execution. So if we go back to our slide,
so
yeah.
The previous thing, so I guess
Yeah.
it's It's at most row times to the negative Sj, I guess, right? The cost of going right.
The cost of going right.
You're accounting for going back left, right?
Yeah.
That only happens with probability.
Sure. I mean, you can. I mean, this. I think you can get rid of rho by conditioning on, you know, either it happened or it didn't, right? Okay. Yeah.
So here you're only counting the going left, and
Yeah.
you're considering the worst case that at some point you're going to go right, which
Yeah.
you might not, because you could finish. You could
Exactly.
go left and then exit on the left, right?
Yeah.
So this is a pessimistic.
Right. This is yeah. So I'm always accounting for this cost, even though sometimes it doesn't happen. Right. And so if we go back to our total calculation, we had the initial part, which summed up to less than 2, the middle part, which we just saw sums up to less than 1, and we had our final cast. So if we add these up together, we get 4. All right, so this is the end of the proof of the main lemma. All right, and now we have just another simple lemma that kind of, these two lemmas together end up giving us the final result. Okay, we know that we do very few compare and swaps in the execution. We can see pretty easily that all the processes do a linear amount of work. And so we know that of this linear amount of work, a linear number are reads, all right? And only a constant number of them are going to be compare and swaps, right? And when you add this all up together, you end up seeing that the total amount of work is going to be n squared. Okay. Now, I promised you a high probability result, and so far we have expectation. Okay? So this final result in expectation directly depends on our lemma that showed the expected number of rights. Okay? But the way we analyze this lemma, each process was independent of the rest of the processes in the system. Okay? So we can actually show that if you look at all the processes together, they're not going to do more than a linear number of cast attempts. Okay? And so once we have this high probability, it kind of carries through automatically in there. Okay? And so, yeah, that's our result. And that's it. Just I guess, a recap of what we did. The first contribution that we made is to say, well, the adversarial model that is usually used is not good enough to analyze things that happen in practice, so we relaxed it a little bit, and we saw, using the exponential backoff example, that we can actually model and reflect what happens in practice, right? And our result for that was that we get n squared log n work rather than n cubed. All right, and then we gave a new protocol that did better than the exponential backoff. So,
Any questions?
yeah.
So I'm curious if you've done any experiments that show even in practice that the adaptive one is at least competitive with exponential or maybe even better?
We haven't, but
Okay.
I think that's a good thing to do.
Because I guess in practice we
Yeah.
don't, the schedulers aren't necessarily adversarial, so I'm guessing that maybe
Right.
exponential works fine.
Yeah.
But
Yeah. So I think one of the interesting directions to go in is to actually write it out, implement it, and see what happens. Yeah. Yeah.
Is there anything special about about having a doubling, or should you do like any sort of geometric update? Like
You can do any geometric update.
And I guess how would it change the results? Like, will maybe asymptotically it wouldn't change, but like what would happen? Like if I set it to like 1/9 times 9 or something like that.
You're asking whether my 4 will become a bigger constant. I mean, maybe. I don't know. Yeah. Yeah. Any other questions? All right. Thanks. Yeah. Oh.
Do you think the n squared work is tight, or do you think you can like? Do you think?
So
you can go lower?
I think it's tight, but we don't have a lower bound. So yeah.
Any other questions? let's thank the speaker again.